This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Hello everyone, welcome to ASCII Radio. Today with me Jeroen Janssens. Jeroen Janssens is the founder and the CEO of Data Science Workshop, which provides on-the-job training and coaching in data visualization, machine learning and programming. Previously, Jeroen was a data scientist at Elsevier in Amsterdam and startups Yplan and Outbrain in New York City. He has a master's degree in artificial intelligence from Maastricht University and a PhD in machine learning from Tilburg University. He is also the author of Data Science at the Command Line, which was published by O'Reilly Media. Welcome to the show, Jeroen.
Thank you, Felienne. Thank you for having me.
The topic of today is data science. Of course, the first question I have, what exactly is data science?
Yeah, so I think if you ask a dozen people what data science means, you probably get back 13 different answers. And so I don't think I can give you an exact definition of what data science is, but the definition that I like to use is simply extracting value from data. And this value can come in basically two different forms. Either it's an analysis that you create, and then the value comes from making a decision based on this analysis, having additional insight into your data or your certain processes or aspects of your company. And the other form in which this value can come is when you integrate data science into your product or your service. And an example that everybody knows is a recommender system in, say, Netflix or Amazon. So that is the definition that I like to use, yeah.
So it's about getting value from data.
Right.
So there are other forms, of course, of getting value from data, and an idea that comes to mind is statistics. Mm-hmm. Statistics is also making decisions based on data.
Yeah.
Is data science statistics or is it something else?
Mm-hmm. It is, so statistics is, as I see it, a part of data science. And to be honest with you, I recently had to look up again what is being meant with statistics. So I opened up a well-known statistics book to look at the contents. And what I noticed there are topics like distributions, hypothesis testing, actually a whole range of tests. And I'm sure that if you have followed a statistics course, that this is what most comes to mind. Things like correlation, doing regression. And this is definitely an important part of doing data science. But it's not everything. If you pick up a typical data science book, then you'll see that it also talks about getting this data in the first place. How to deal with data that is messy, that is complex, and how do you get it into the right shape? How do you create a visualization out of this? So in that sense, they're not equal, but they're definitely related to each other.
Yeah, so you're saying that statistics is a part of data science. What are other parts of data science that aren't statistics?
Right. So here I always like to use a very pragmatic model of what data science is. And this is one created by Hilary Mason and Chris Wiggins back in 2010. And they say they proposed the ASCII model, where ASCII is an abbreviation of 5 steps, right? So, and they say that data science basically comes down to obtaining data, right? Without any data, there's little data science that you can do. And then rarely does this data come in a form that you can readily use. So you have to scrub this or clean this. Then it's time to explore this data. What does it look like? Can you compute some aggregate statistics? Make some quick visualization. And this could be the result of itself, right? If you're producing an analysis, putting all the data that you have in a visualization could already be a valuable thing. Sometimes you want to go a step further, and that is the modeling data part of ASCII. So this is where you may want to apply machine learning or statistics, right? Just to come back to how those two are related to each other, to generate classifications, to make predictions into the future, to see whether there are any clusters or patterns in your data. That's why machine learning is often also known as pattern recognition. And then the last step, according to the ASCII model, is interpreting data. What do your results mean? How should you interpret them? How do you communicate them back to your colleagues or your peers or your manager? And of course, these 5 steps, it's never as easy as this. Sometimes you do these steps in parallel. Sometimes you have to go back because you notice that you're missing some data or you made a mistake early on. But that is a very pragmatic, I would say, set of things that you need to do in order to do data science.
Yeah, so you're saying data science is broad. It's not just analyzing the data or doing statistics. It's also obtaining the data, scrubbing and exploring. It's all part of the big umbrella of data science.
Right, that's right.
And sorry.
Yeah, no, well, I was just thinking it's actually too broad. And that's also why I think that there is this term data science. I'm not a big fan of it. I don't really like the term science in data science, but so far I haven't been able to come up with a better term.
Yeah, and sometimes the term it is there. So even if we don't agree, it's something that everyone says. But I do want to come back to what you're saying, because one of my questions I had in mind was, being a scientist myself, what is science about it? Can we apply it in a business context, or is this really something only a scientist would do?
So I think data science is definitely applicable in a business setting. In fact, this is one of the few fields where I see the industry and academia and business coming together. So because businesses, first of all, have a lot of data, and they also have a lot of money to hire the people to work with that data. And well, data science doesn't necessarily have to be scientific at all. If you build a recommendation system, right, that in itself is not really scientific, right? If there's no hypothesis associated with it, if you're not doing, so what is science really?
That's a bit too deep, maybe, for this episode. It is
perhaps a bit too deep, but it is. There's definitely the part where you, depending again on the type of data science that you're doing, either analyzing or building something. It could be that you have an hypothesis, that you experiment, that you make observations, draw conclusions from that, but that's not necessarily the case. And maybe that's the biggest difficulty I have with the term, because it is that there are these two categories. There is a group of analyzers, and there's a group of builders, and of course they're all and this is not as binary. Of course, there's a whole range in between the two, and then there's everybody complaining that everybody else is calling themselves data scientists. There's that. So there's definitely a lot of hype about this term, especially if you combine it with the term big data, which I don't like very much. But I don't think that there's no denying in that there is that recently certain things have come together in a field that we call data science, which is only becoming more and more popular.
Why do you think that is happening now? Because the ideas, data analysis, has been there for a very long time, and so is statistics, and even R is already a relatively old programming language. Why do you think it's in fashion now? What has created this hype, as you call it?
So indeed, many of the techniques and ideas that are in use in data science when you work with data are several years or several decades old. And in recent times, what has changed is the amount of data that we are collecting and the amount of computing power that we have. I think those two together, they allow for new techniques to be used. Take, for example, deep learning, which is yet another very popular thing within artificial intelligence and data science in recent years. But the ideas on which it's built has been around for much, much longer. I think now that we're able to process so many data, also with the arrival of GPUs, all of a sudden this is starting to become really, really popular. Companies are starting to notice that this is an important thing to have, that they should have data scientists, entire teams of data scientists, entire departments, and in turn, others have noticed that there are high salaries associated with this. I think, it's...
Yeah, once you have a critical mass of companies are interested in it and education get interested in it, and then it sort of adds up to each other.
Yeah, education is another good example. In the US, but also here in the Netherlands, we see more and more education forming around data science. There are masters of data science nowadays. Bachelors of data science are coming up as well. So once again, it's interesting to see that both academia and business are moving ahead in this.
Another topic, of course, that's quite hot, and we had a ASCII radio show about it, show 286, is machine learning. And you already mentioned machine learning earlier, and also you just mentioned deep learning. How is data science related to machine learning?
Yes. I think in a similar fashion that statistics is related to data science. In fact, you could consider machine learning to be statistics on steroids. So combine statistics, right, with all this computing power and data to learn from. And so if we go back to the ASCII model, then the letter M stands for modeling, and this is exactly where machine learning comes in to play. Sometimes there are machine learning algorithms can be used to clean up your data. For example, when you have outliers, right, very extreme values in your data, or when you want to reduce the number of features in your data. Say, for example, you have a digitized image, and you have lots of values that you need to reduce in order to work with that. That's another area where machine learning can come into play. Yeah.
Nice. I like this quote that machine learning is statistics on steroids. That because we have more power, more computational power, more data, it gets easier to do statistics. Let's zoom in a little bit, because we've covered the big definition of data science, but suppose I want to learn data science. I'm a programmer, but now I really want to learn more about data science. What are some of the core principles and ideas I need to learn about?
So for starters, I don't think that anyone should set out to become or learn data science. Instead, aspire to tackle a certain problem that involves data, and then figure out which skills you need to acquire in order to solve that problem. Again, because it is so broad. There are skills, relevant skills that fall in the category of data manipulation, data engineering, up to data visualization. Again, statistics. There are people who are better at machine learning. Others are better communicators. There is no typical data scientist. That's why you usually see these data scientists working in teams, because you need all those skills, right? Very often, but nobody has all these skills equally well developed. Nevertheless, if you want to learn more about data science, I do have a couple of books perhaps that are interesting to read, depending on where you're coming from, and taking into account that this audience, are mostly engineers. One book or there are a couple of Python-based data science books that I particularly like. One is called Python for Data Analysis by Wes McKinney. It assumes Python. This really goes into some popular packages that are used within the Python ecosystem, such as NumPy, SciPy, Pandas, and so forth. Another book that I like is Data Science from Scratch by Joel Gross. And I like this book because it uses pure Python and then builds up several kinds of algorithms, so mostly machine learning algorithms for classification and regression and so forth. From scratch, as the title implies. If you want to move more into machine learning per se, then I can recommend Python Machine Learning by Sebastian Rushka. Covers mostly a package called scikit-learn, a Python package which contains a lot of algorithms and related tools and techniques for doing machine learning in Python. But this is all assuming that you have Python as your go-to language. Right, so of course there are, there are basically too many resources. MOOCs, if that is your thing, right? If you like to watch videos and do those exercises, and to be honest, I've never followed a MOOC myself, so maybe it's just best if you Google for this.
Sure.
Yeah.
We'll at least make sure we will include the links to those books you mentioned in the show notes. So if you want to check out those, then we'll definitely make sure that it's easy for the audience to get to those books.
Yeah. There is one resource that I could mention, and there is a woman called Renee. I forgot her last name, but she has a Twitter account, Becoming Data Sci, or Becoming a Data Scientist, and also Data Science Renee, if I'm not mistaken. But she aspired to become a data scientist a couple of years ago, and she has been documenting this entire process, and I'm sure she has much more resources that I could ever come up with. So we'll include a link.
Yeah, we'll include a link. Now, I've heard you mention Python a bunch of times in all those resources, so let's talk programming languages.
All right.
Are you endorsing Python here as the best programming language for data science, or is there something else out there?
The answer is no. I can certainly endorse Python, but it's not the best language.
Okay, let's make it a little bit more abstract then. What are characteristics that a programming language has to be good for data science? Are there any?
There are several languages. And again, it depends on whether you are analyzing or whether you are building. So let's look at analyzing. When you're analyzing, you need to be able to play with your data. You need to be exploring what your data looks like. You need to be able to quickly make visualizations, summary statistics, and then move on. So this is a very ad hoc way of working with your data. In that sense, I think it's important to have a language that gets out of your way, that doesn't let you worry too much about typing, about boilerplates, about instantiating all these classes up front, right? So languages like Java are not suitable, in my opinion, to do analysis. Languages that are suitable for this is Python and R. These two languages, I would consider them scripting languages because you can accomplish something in one line of code, right? And this is what you want. You want to be able to, with minimal typing, you want to get results. Also, what these languages offer is a REPL, is a read, eval, print loop, so that you can try out individual commands, see what the outcome is, and move on from there. Now, for those two languages, you would rarely work on the REPL that they offer themselves. So for Python, many people tend to work in a Jupyter Notebook, but it's a similar idea where you can execute individual code cells. And this could be one line or a couple of lines or an entire function. And what's nice about Jupyter Notebooks is that you not only have your code, but you also have the output of that code intertwined in between the code cells. So this could be a result, a table. It could be a figure. This could be regular text with markdown text, right? So this really allows you to build up this document for your analysis.
Yeah, so our audience might not be exactly familiar with what a Jupyter Notebook is. Is it like a REPL or is it something different?
So a Jupyter Notebook runs in your browser, and what you see is first you see this little gray area in which you can type Python code. So you would do your import of the packages that you want to use, and then you can execute individual code cells. So you don't have to write up your entire program and then run it and then go back to the original code. No, you stay within the same environment and you can iterate from there. So it's and because you have your results immediately beneath the code, you immediately get feedback, and then you can move on from there. So you build up your code incrementally. And this is a very different approach from coding something, optionally having to compile it and then run it from scratch. Right? This breaks your workflow.
Yeah, and that for me still very much sounds like a REPL. The way I see it, I think is a difference is that in a REPL the output would mainly be text or only be text, whereas a notebook you could also have different things as output. Am I correct?
Yes, that's correct. So it's not just text. It's your statistical data visualization, maybe as simple as a histogram. It could be as complex as an HTML widget which shows you an interactive map of something. And this is possible because it runs in the browser. If you're working in a REPL from the command line, then the output is by necessity text. Yeah. Although there are flavors in between those two. Yeah,
you could always use text, of course, as a visualization by using something like an ASCII table.
Yes.
Of course, that's not as nice as a Jupyter Notebook where you have nice visualizations and graphs and charts.
And R, so something that we should talk more about as well, because these two languages are both really popular, offers something similar called R Markdown and R Markdown notebooks. There the experience is slightly different, but conceptually you have your code chunks or code cells and the output in between those code cells.
Yeah, let's talk about R a little bit more, because I guess most of our audience is familiar with Python or other scripting languages, but R is a little bit different in that it is a programming language. It's not a GPL, a general purpose programming language. It's a programming language that has a narrow scope, which is statistics and machine learning. Is that correct?
That is entirely correct. So R was created by statisticians, for statisticians, and because of that, it has certain characteristics which may seem odd at first to programmers who are more accustomed to a language like Java or Python. But because it was created by statisticians, it has become a very popular language within the data science community. In fact, I think that R and Python are the two most popular programming languages. In the end, you can do pretty much the same with the two. But Python, to me, this is very personal, to me feels more like a programming language, and is also easier to understand as a programming language. And because it started out as a programming language, Python that is, it has a much broader scope when you look at its packages. Right? If you look at PyPy, the repository for all Python packages, it's not just data science. In fact, most of it is not data science, and is also covers anything from API development to building your own web server, creating your own game, authentication, interacting with databases, and so forth. R, on the other hand, has, last time I checked, nearly 12,000 packages as well. So that's not a not a small number, but it's mostly geared towards working with data. Recently, this has changed somewhat. R is getting better support for working with databases, creating your own API if you wanted to, and because it operates more on a higher level. If you work with a package in R, it offers very convenient functions. It feels smoother to work with R. But when I'm working in Python, it feels more like I'm creating this robust piece of software. Again, this is entirely personal, and the choice between the two depends, well, first of all, on your personal preference, but more often, what are the others in your team using, or other teams. So I once created this great model for a client. It was able to do some sort of classification, and now we wanted to move that into production, meaning it had to serve an API with which the website would integrate with. So I had to talk to the API team. This was a large telecommunications company. Well, long story short, I had to re-implement the thing in Python. That was not a big issue, but it's an example that when you want to do things in production, Python is most often the better choice. Yeah.
But as you said, sometimes you don't have the choice. So suppose we have to work with R. You just mentioned that it has some odd characteristics. Can you name a few that we should be prepared for if you are working in a team that's working with R?
R has a different way of working with memory. So it copies on change. And people who are first getting familiar with R, who already know another programming language, tend to use a lot of for loops, right, to incrementally build up their data frame, which is a very important data structure. It's like a table, and this causes memory issues, right? This is one example. It has a different way of looking up values of variables. And this is actually something that is an advantage, I would say, of R, is that for a lot of functions, you don't need to quote your values. And this may seem like a trivial thing. So let's say you have some data frame, a long table with rows and columns, and you need to refer to one of those columns. Then in Python, if you would do this using the pandas package, you need to quote everything. That's simply how the programming language works. But in R, it's a technique called non-standard evaluation. You can simply write those column names without quotes. And this, again, may seem like a trivial thing, but it makes working with the language and working with your data just a little bit easier and more comfortable.
Yeah, so to summarize, R is closer to the world of a statistician. It makes some things easier. However, it's not a full programming language. There, Python might be more suitable if you want to do a broader range of things.
Yeah, I would say in a nutshell that is true, but it is good to know a little bit of both and know which one would work best for a particular project, and then decide, based on the requirements of that project and the people who you're going to work with.
Yeah, of course, sometimes you just don't have the choice.
Yeah.
But it's good to be informed.
Yeah.
Okay, that's enough, I think, about programming languages, because your book is called Data Science on the Command Line, which maybe indicates we don't necessarily need a programming language. There's enough we can do on the command line. What are things we can do on the command line? Can you share a few things that we can do there without a programming language?
Yeah, so it remains to me, after it's been out now for 3 years, it remains to me an odd juxtaposition of terms. On the one hand, we have this young field, as we've discussed, called data science, and on the other hand, we have technology that's over 40 years old. Right? And I decided to put those two together in a book because the command line, well, it offers a REPL, right? This read, eval, print loop, so we can type our commands and immediately get a result. But another reason why the command line works so nice is because it has all these little command line tools which are designed to do one thing, but do it really well. And since they are all working with a text interface, they can work together really well. And this gives you a lot of flexibility. And as a result, you're able to, it could be, right, depending on your problem, that you're able to get it done with just 1 or 2 lines at the command line, which would otherwise take you, say, 10 to 20 lines of code in Python or R.
So you mentioned there are a few cool command line tools. Can you give some examples of tools you could use on the command line?
Yeah, well, there are many of them, and the book alone discusses over 80 command line tools. And a couple of tools that I like, well, first of all, let's curl is of course, it's the Swiss Army knife of downloading things from the internet. So that would cover the obtaining data in a lot of cases. If you're working with JSON data, let's say you're querying some API, then JQ is a command line tool that has come out in a few years ago that is particularly suited for this. If you want to speed up your pipeline, say you want to distribute it among multiple cores or machines, then GNU Parallel is a very effective tool for doing that. Let's see now. If you still happen to be working with XML, I can recommend XML Starlet. If you need to scrape HTML, right, sticking to obtaining data, right? Let's say there's no API available, you need to scrape, you need to extract certain elements from HTML, then pub is interesting. And you know, those are just a couple of examples. Now it's perhaps also good that we include a link to a Docker image that I created for my book, which contains all these command line tools, and that way you don't have to spend an entire day installing all these tools. One that just came to mind is a CSV kit, which is a suite of command line tools related or that are able to work with CSV data. And actually, I have an interesting announcement to make.
Go ahead, we love scoops.
And that is that my book, Data Science at the Command Line, is now available online for free to read. So I'm very happy about that myself. So if you go to datascienceatthecommandline.com, you can now see an HTML version of the book.
Awesome. We'll be sure to include that in the show notes as well. And also the Docker image you mentioned. That will save people a lot of work if they want to explore this. So how do you go about this? Suppose you have some fluency with all these command line tools. How do you package them together in a working thing?
And by a working thing, I guess you also want something that is somewhat robust, somewhat reproducible.
Yeah, this is actually, especially reproducible is where I was going, because if I have a Python file, then if I get new data, I can run the file again. But if I do it on the command line, it's gone if I close the command line. How do you deal with that, exactly that robustness and that reproducibility that would come automatically if you would have a Python file?
Right. So indeed, when you start working at the command line, it's typing commands, and then, well, they tend to be gone, right? You're not working in a script just yet. But to a certain extent, this is still possible. You can go back into your history, collect all the commands that make sense, clean them up, put them in a script that would work for short scripts. that are designed for a very specific task. Maybe you would include some bash programming, but as soon as I need some more logic in my script, I tend to go to a programming language myself. And that whether that's R or Python, right? That depends. But yeah, the command line is definitely not suited for everything. It's especially when you're in that first phase. You just got a new data set. You have no idea what it is, and you need to quickly have a look at things, compute some things, count certain lines. I don't know. Maybe you're working with log files of some server, right, which has nothing installed. That would be a good use case. That's where the command line can really shine. But as soon as you want to build something that is robust, that you want to maybe even share with your colleagues, I would that you want something reproducible and that you understand 6 months down the line, I would use a programming language in those cases.
Yeah, so the command line, if you were talking about the ASCII model again, would be early in the ASCII model where you're obtaining, scrubbing and exploring data. As soon as you start modeling and analyzing, you would go to a real programming environment.
Right, mostly yes. The good thing is most times you can go back and forth in between the two. It's if you look at an entire data science project, it's composed of all these little sub-problems. And it's up to you to decide which tool gets the job done best, right? Whether that is the command line or Jupyter Notebook or pen and paper, doesn't matter. But as long as you get the job done.
So what you're arguing, I think, is not do all your stuff on the command line, but more be aware that there are these awesome tools on the command line that can help you do things more efficiently, but don't use them forever.
No.
That makes sense.
That's correct.
Let's talk about that robustness and reproducibility a little bit more, because I think there are some interesting angles that make data science different from software development. For example, how do you go about version control? If you're version controlling in software, you just have your source code. Whereas I think if you're doing data analysis, you have to do version control of your source code, but also of your data. Because if your data changed in the meantime, but you're running it with the same source code, you might still get different results. Are there specific things or specific methodologies you use in doing version control in data science? Or is it just a regular software project and you do everything similar?
I think ideally you would tend to use, or you would adopt the best practices that engineering has already come up with, such as version control. And it's of course perfectly fine to version control your code. Your data, on the other hand, I wouldn't put my data in a GitHub repository per se. Rather, I would have the code that gets the data, whether that is from some API or some database. I would have that part of my code, so that is also versioned. You want to eliminate all these manual steps, so that it's not a matter of, okay, I can interact with this database using Excel, and then I just need to change a few columns here. Let's export this to CSV, and then my script can run. No, you want to version control all the things.
Yeah, sure, all the things.
Yes.
But I was thinking, I mean, you have this data set and you run your analysis and you say, okay, we have to, buy these stocks or sell these stocks. And the next day your boss comes in, says, okay, show me how you got this result. If you use a tool that just scrapes data, maybe you get a different result, a slightly different result. Do you somehow want to track what data you ran what analysis on, and how would you do that? Or you're saying there is no such thing as yesterday's data, we don't care about that anymore, we would just run the whole analysis based on fresh data, and that is the new conclusion.
Yeah, interesting point. In that sense, I would definitely make a copy of yesterday's data and make sure that the code is able to accept a parameter such as from and to. Yeah, no, this is a very important part. It reminds me of a story when I started working as a data scientist in 2012 at a startup in New York. And when I came there, I was the first data scientist. I noticed that all the engineers were throwing away all the raw data, right? So I mean, I don't blame them. I mean, storing all that data is expensive, and they were computing aggregate statistics to report to our customers, and that's that. But well, of course, as a data scientist, I decided to change that and to make sure that all the raw data was properly backed up, and so that we could redo or backtracking or backtracing. I believe it's sometimes called that you're able to run your algorithm on older data as well.
Yeah.
It could be that you're improving your existing algorithm, especially with machine learning algorithms. This might be the case, and you want to compare multiple versions of that algorithm against the whole period of data. So having those two parameters, a from and a to, actually makes a lot of sense.
Yeah. So generalizing from that a programmer or software engineer that would become a data scientist or do more with data science probably has to change our mindset a little bit into seeing data, especially raw data, as something that's important. Because if you're a software engineer, you're probably mainly focused on the code and not so much on the data, as exactly as you're describing. So it's important, I think, to keep in mind if you would move more towards becoming a data scientist.
Yeah. That's where both groups, if we can make that harsh distinction.
Yeah, I know it's a spectrum,
but that's where they can learn a lot. That's where they can learn from each other. I believe that data scientists can learn a lot from engineers when it comes to coding styles, version control, documentation, packaging, all those kind of things, and I'm sure there are plenty of things that engineers can also learn from data scientists.
Yeah, something you haven't mentioned in the long list of things they could learn from us to make the distinction even more clear is testing. So if you're a data scientist, how do you go about testing your models? Of course, you have your real data to test certain assumptions on, but are there things, do you write unit tests or integration tests if you're a data scientist? How does that work?
So I believe there are several types of testing. In the machine learning world, when you say testing, what you do is that you divide all the data that you have, all the labeled data. So let's say you have lots of API calls with a certain label, like valid or invalid, or you have a whole bunch of fruit saying, okay, this is an apple and this is an orange. What you then do is you divide this data set into a training set and a test set. You train the model on the training set and you test it, you let it make predictions on the test set, and then you compare the outcome from the machine learning algorithm to those true labels, right? Valid, invalid API call, or apples and oranges when it comes to fruit. And that will lead to a certain performance. That is one type of testing, but then you're talking about is algorithm A better than algorithm B? When you said unit testing, that's a different kind of testing, but important nonetheless. I would use say mock data, right? You have a certain set of data on which you know the outcome, right? Maybe not necessarily the end predictions, but maybe intermediate computations as well. And that would be a way to check whether the code or whether your algorithm is still working correctly.
And is this something that's done in practice?
Well, is unit testing done a lot in software
Absolutely.
projects?
What are you talking about?
Well, it's one of those things that data scientists are not really fond of. It's kind of like a documentation thing. It should be done more often. Yeah, definitely.
Yeah, and a final form of testing, or there are many forms, but something else that might be interesting is regression testing. Understanding, especially since the code might be stable, but you're getting more and more data, which is changing your model. Is this something that's done, checking what way a model is going with automated tests? I mean, you yourself said automate all the things.
Mm-hmm. Yeah. So regression, so tracking the performance of your algorithm in the long run.
Yeah.
And then it could be performance in the sense, how long is it taking to compute something, right? That's more from an engineering point of view. And the other thing that you probably want to test is it still giving good results?
Yeah.
So the first one I would say is quite straightforward, where you can measure how long an algorithm is taking. And if you then store that raw data as well, then you can do some analysis on that, of course. Whether the algorithm is still making the right predictions, right, still has a good performance in the long run, that's a very difficult subject, and especially when this algorithm has an effect on the real world, right, which tends to feed back into itself. And it could be that because of this algorithm, the data, right, the things that you observe of your users, your customers, that is changing. And so I don't really have an answer for this.
Yeah.
But it's definitely a complicated thing. There is an important paper related to this. We'll include the link to that one.
About regression testing machine learning.
Yeah, about the side effects that machine learning can have. If I'm not mistaken, it's called the technical debt of machine learning. Could be somewhat different. We'll look it up.
Okay, we'll look it up and we'll make sure that it's in the show notes. One more thing you said about documentation that made me think about open source, because lots of software, of course, is nowadays open source. It's on GitHub. People can see what is happening, even sometimes within companies or within organizations. Do you see a similar movement in data science where these data science models are also shared as open source such that they can be reused and then also documented? Or are these things mainly happening in companies that don't want to share their data analysis models?
Okay, so let's distinguish between the tools and techniques to build such a model and the models themselves. First of all, in general, I definitely see a positive trend towards open source within data science. That's also why Python and R, both open source languages, have become so popular, right? And all the commercial software, right, is losing this battle.
Like who's losing?
MATLAB, for example. During my PhD, or 75% of it, I was using MATLAB, and outside, it took me a while, but I realized that once I got outside of academia, it's not used that much at all, which is not that surprising if you consider how expensive it is to use. These days, people who want to learn something will tend to go for the option that is freely available, that is open source. So if companies are looking for smart people to hire with a certain expertise, certain experience, they will most of the time have experience with things that are open source, and less often with something that is expensive and commercial. Also, with open source, there tends to be a bigger community around it. If you look at the communities around Python and R, those are so much bigger again than what commercial counterparts have at this moment, and I think that this will only become more clear. And then, open source models, that is typically something that a company is not so willing to share.
And with model, you mean the result of the Python script or R script, or also the script itself?
The former. So they have typically some data that they have collected. They have applied an algorithm to it, which produced a model. And this could be their competitive advantage, right, to do something. And so in that sense, they could be willing to share the code that led to that model, but not the model itself.
And do they typically share the code that led to the model? Is this something that happens, or are those things also felt to be proprietary?
You do see more often that the big companies like Facebook and Microsoft and Twitter, that they are sharing algorithms, right? And maybe even pre-trained models. But this is definitely not everything that they are using. For example, language models that have been trained on lots and lots of data. Every now and then you do see that these companies share those models. But more often they share the underlying code that generated that. For example, Facebook has open sourced a package which is available for both R and Python, interestingly enough, called Prophet, which allows you to make forecasts based on time series. I like this package a lot, and I think it is great that a company like Facebook is willing to share that with everybody else.
Yeah.
And then this is just one example of many. Definitely.
So there is some sharing going on in terms of the source code, but obviously not the data and often not the trained models.
Mostly, yeah. More often than not, the data is kept secret.
Yeah, that makes sense.
You do tend to see more open data, but those are exceptions. Yeah.
Okay, Jeroen, that's everything I wanted to ask. Thanks a lot for being on the show.
My pleasure.
If the audience wants to know more, where can they learn more from you?
All right. Well, I'm on Twitter for starters. We will add the link to the show notes.
Absolutely.
It's too difficult to pronounce, actually, that handle. And if you think like, hey, I want to learn more about data science, and you're not alone, you're with an entire team within your company, then it's worthwhile to note that I also give workshops in these kind of things. Workshops in R and in Python, or how to use the command line for doing data science. And if you would like more information about that, the website is datascienceworkshops.com.
Which we will, of course, also include in the show notes, and also a link to your book that is, again, freely available for everyone.
Yeah.
Anything else?
No, that's about it.
Okay.
Thank you very much.
Thanks again for being on the show. This was Felienne for ASCII Radio.
Thanks for listening to ASCII Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at sci-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at sciradio.slack.com. You can also email us at team@sc-radio.net. This and all other episodes of ASCII Radio is licensed under Creative Commons License 2.5. Thanks for listening.